So let's solve this one first. So this is a hexadecimal number. This is the ones place, the 16s place, the 256 place, the 4096 place. So this is this. Huh?
1, 2, 4, 8.
Nope, that's for base 2. So base 2, this would be the ones place, the twos place, the fours place, the eights place. Base 10, this is the ones place, the tens place, the hundreds place, the thousands place. Base 8, this is the ones place, the eights place, the 64s place, the 64 times 8, what is that? 512? Yeah, 512's place. All right, so this is base 16. So this is 16 to the zeros place, 16 to the ones place, 16 to the twos place, 16 to the threes place. All right, we kind of saw this in action last class, and then you finished it with your homework assignment this time. So last class we wrote binary string to decimal, correct? And then we modified that for octal string to decimal, where the only thing we had to change was the multiplier for place, correct? Instead of multiplying, place started off at 1. Instead of multiplying it by 2 each time through, we multiplied it by 8. I think we also write decimal to decimal? At some point when I was teaching this, we converted decimal to decimal and saw it work, right? You know, we do the exact same procedure regardless of what base we're converting. Just the only thing that changes is the place. The homework assignment was to convert a hexadecimal string into a decimal string. The only twist that we added to what we wrote in class last time is how do you handle things like A's and B's and F's and those guys? You know, non-numeric things, right? How do we do the conversion so we were doing the correct math? All right, so this F is in the ones place. This 1 is in the 16s place. This B is in the 256 place, and this A is in the 4096 place. So this is 16 to the 0, 16 to the first place, 16 to the second, so this is 16 squared right here, and this is 16 to the third. All right, and F is actually a 15, so that's 15 times 1. A B is actually an 11, and A is actually a 10. All right, so this is a 15. This is a 16. That's a 2816. And this should be 4960. Like that. Then we add all those guys together. So that's going to be 4960 plus 2816 plus 16 plus 15. And that's 43807. So that is the decimal version, 43,807 of the hexadecimal value AB1F.
Can you go back to the slide where you had like the values of each one, where like before you did all the calculations, or was that on the second?
Like your notes?
Yeah, where you just had where A equals.
Are you saying when I had this was when I said this was an F?
Oh yeah, that's yeah.
Yeah, so I mean, I think what you're looking for is I mean, it'll seem.
You already did that.
Yeah.
Okay.
Here, I'll just write it real quick so everybody has the reference. It'll seem dumb once you see it because it's a direct mapping, but just so you, let's just call hex mapping so everybody sees it. So an A is a 10, a B is an 11, a C is a 12, a D is a 13, an E is a 14, and an F is a 15. Make sense?
Yeah.
So in hexadecimal, it maps like that. Now that's base 16. If I said, for example, a fair question for me to have asked today would have been this. I don't know, let's just do like an S. Okay, from base 35 to decimal. That would be a fair question. You don't do it any differently. This is the 35 to the zeros place. This is 35 to the ones place. This is 35 to the twos place. This is 35 to the threes place. So if I were to say convert this number to base 35, let's just do it real quick, but we'll do it in a separate slide as an example.
Okay, so it's negative 35.
So, well, I was trying to put base 35, but let's not confuse it. So base 35, this is S times 1, because this is the ones place. And we'll give values to it here in a second. Then it's 1 times 35, because that's the 35 to the ones place. 35 times 35 is 1225. So this is B times the 1225's place times 35 is the 42875's place. And that's an A. Okay, so S, where does S come in the alphabet? All right, that's the 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. So this is a 28 times 1 plus a 1 times 35 plus an 11 times 1225 plus a 10 times 42,875. So that's going to be a 28 plus a 35 plus 11 times 1225 is 13,475. 13,475 plus 42,870. Well, so that's 442,288. 442,288. So AB1S in base 35 is equal to 442,288 in base 10. All right, so the conversions are always identical. The place changes depending on what the base is. That makes sense? So this would have been a fair question to ask, and it would have been the same question that I did ask, but most of us at this point probably would have thought this would have been a ridiculous question, even though the difficulty, well, other than the numbers being huge, the difficulty wasn't worse. But hopefully this kind of finished connecting the dots for you, that all the bases are the same until we run out of letters. All right, so when we go back to this thing here that you asked for, this is the hexadecimal mapping, but we can just keep going. J, K, so on and so forth. So G, if it existed in the base, would be a 16, and H would be a 17, and I would be an 18, a J would be a 19, so on and so forth. If it was a legal character in the base. So a G is not a legal character in base 16. It is a legal character in base 17. Base 16, the legal digits are 0 to 9, A through F. Okay, because it's 0 to 15. Base 10 is 0 to 9. That's our base system, right? Base 8 is 0 to 7. Base 2 is 0 to 1. So it's always 0 to the base minus 1 for the legal characters in that base. Does that make sense? So up to base 37, we can represent all the values. That's 0 to 36, which would give us 0 to 9, then A through Z. Then we start having issues, right? So anything beyond base 37, we don't have the characters to deal with it. Okay, we need a different alphabet. I think somebody maybe when I first mentioned that, somebody maybe suggested, oh, we can use lowercase letters. The issue is that in the standards there is no standard necessarily about upper or lowercase letters being used for hexadecimal, which is our common base 16 is a fairly common base in computer science. So an uppercase A and a lowercase a are often interchangeably used. I think somewhere the standard probably indicates there should be uppercase letters, but they are in practice used interchangeably. Therefore, we can't just say, well, the uppercase letters come first, then we go to the lowercase letters, so now we can support an additional 26 bases, right? We can support base 47 and base 57 and up to base 64, I guess. That doesn't fly. Okay, so we would have to have invented symbols. So technically, I guess we could use the Unicode character set, right? We have the Unicode character set as our possible characters, minus the 0 through 9, since they are already taken. So we could have up to base 65,527. We could support up to that base if we use Unicode as our... Now we're getting into numbers that calculators are going to have issues dealing with. All right. Now, having said this, if we just look at this guy, even though we don't count this way, AB1S is far easier to, it's far more compact than this giant number, correct? So that's the advantage of having larger bases. Now, that's the generalistic advantage. Now, the reason we use base 16 in computer science is it has a base 16, base 8, base 2 have conveniences in computer science for creating, groupings. So, for instance, if we go back to this guy, and this used to be, I have an F there? Like that. Okay, so a question I could ask you to do before we solve today's homework. And this one should scare you a little bit right off the bat. Hex to binary. Okay, so if I said convert AB1F from hexadecimal to binary, our natural inclination might be, okay, well, let's first convert it to decimal. So now I have that number, right? So we'll convert it to decimal first, and then I'm going to say, now I have that decimal value, let's convert that to binary. So we keep dividing it by 2 over and over and over again until we get the binary equivalent, right? Well, that's going to take, there's a lot of zeros and ones that are going to go into making 43,807. That makes sense? But we could do it. It would be a long, drawn-out process. The reality is this is actually very, very, very easy to do, to go from hex to binary. Each of these values, A, B, 1F, A, B, 1F, can be written in something called a nibble, a 4-bit number. So a nibble is a half of a byte. Okay, so an A is a 10. So that's 1 in the 8th place, a 0, a 1, a 0. A B is an 11. So that's 1 in the 8th place, a 0, a 1, a 1. A 1 is a 1, so that's 0, 0, 0, 1. And an F is all ones. That's an 8 plus a 4, which is 12, plus a 2, which is 14, plus a 1, which is 15. So 1, 0, 1, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 1, 1, 1.
And that's when it starts to get to the point.
So that is the binary version of this. And that's far easier to solve than doing convert to decimal, then convert from decimal back to, that makes sense? All right, so that's an advantage of hexadecimal, and that's one of the reasons why hexadecimal is popular. You're able to take each of these individual hextets, is what they're called. They're not digits because hextets support 0 to 9 and A through F. And then you can convert them to binary very easily by taking each one of them and representing it as a 4-bit number. Similar trick exists for octal values. So if I create another slide, and what are the legal digits in octal? 0 to what? 0 to 7. Okay, so octal is base 8. Legal digits are 0 to 7. All right, so that means I can pick any number that's made up of the characters 0 to 7. So let's do 1027. Octal to binary. All right, the largest value in octal is 7. How many binary bits does it take to represent a 7? What's a 7 in binary?
101, I think.
It's 111. So 1 in the 4's place, 1 in the 2's place, 1 in the 1's place. So 4 plus 2 plus 1 is 7. So you could do the exact same thing we just did with hexadecimal, but in packs of 3. So a 1, a 0, a 2, a 7. This is 0, 0, 1. This is 0, 0, 0. This is 0, 1, 0. This is 1, 1, 1. So the binary version of this octal number is 0, 0, 1, 0, 0, 0, 0, 1, 0, 1, 1, 1. That's the binary version of this octal number. I realize there's a lot of zeros and ones and things like that we're throwing around, but when you break your octal number into its individual parts, I think these are called octets. Octets is the official word for that. Humans, we typically will call anything that looks like this a digit, right? Even though the second you start getting things that aren't base 10, it's technically no longer a digit. Digits for base 10. So these are 1, 0, 2, and 7. Those are all octets by official standards, I guess. A, B, 1F for hexadecimal, these are all hextets by official standards. Call them whatever you want. I'm never going to ask you what's the official name of a single character in hexadecimal or decimal or anything like that. If you want to think about them as digits, that's fine. Doesn't matter. All right? So each of these guys can be represented as a single 3-bit binary value. So we'll go ahead and we'll represent the 1 as a 0 followed by 0 followed by 1. This is a 1 in the 1's place, a 0 in the 2's place, a 0 in the 4's place in binary. Then the 0 number, that's all zeros. Then 2, that's a 0 in the 1's place, a 1 in the 2's place, a 0 in the 4's place. A 7 is a 1 in the 1's place, a 1 in the 2's place, and a 1 in the 4's place. And then you just write all those bits next to each other. And that gives you the binary value of that. But you do need to make sure you spell it out. You can't just say a 0 here is just, oh, that's just a 0. Because those 3 zeros which lived right here, those took up places, right? You know, if we shrunk that from 3 bits down to 1 bit, those are 2 powers of 2 that we're losing in terms of the full value of that big long string. So if you're going from octal to binary, it's always 3 bits for the representation of each octet. When you're going from hexadecimal to binary, it's always 4 bits to represent each hextet. Why is that? The legal digits in hexadecimal are 0 to 15. Well, how many bits do we need to represent a 15? We need 4, right? We need an 8 plus a 4 is 12, plus a 2 is 14, plus a 1 is 15. So we need a total of 4 bits to represent the largest hexadecimal hextet. Does that make sense? So on the surface, it seems like it's a trick, but the reality is it's kind of the punchline behind why octal and hexadecimal have become popular. Well, not popular. They are functionally sensical choices for our numbering system in computers. Does that make sense? Since at the baseline, anything we do computers, it's digital, we're going to have zeros and ones all over the place. That decision was made for us. Okay, when we decided we're dealing with digital logic, on or off, 0 or 1. Now it's how can we more conveniently represent zeros and ones in chunks, in manageable chunks that we can move between quickly. Moving between binary and hex is very easy. So, for example, if I were to give you a quiz that looked like this, and I would probably expect something like this coming up relatively soon. So we're going to say scary looking binary number, and I say binary to hex. Okay, right off the bat, you're going to say, well, that sucks. Right? You're going to look at it and say, when you see a wall of zeros and ones, you immediately break that down into kind of assuming that it's very difficult.
Can we just do a break between every 3 numbers?
Almost. In hexadecimal, it's every 4. Yeah, if I were to say binary to octal, then it would be every 3. Yeah, but since I've asked you to go to hexadecimal on this one, we know that we need a nibble. That's the nibble is the official term for 4 bits. A nibble is a half of a byte. A byte is 8 bits. A nibble is 4 bits. All right. I also won't test you on that. Just it's a thing. Okay. So since I've said we're going to hexadecimal, you know that each of these guys, I can take these in packs of 4. Now, always start with the right-hand side because you might have to, depending on how many bits you're given, you might have to pad this out with zeros in front to give you your last nibble. All right? Is the value I have written right there any larger than that value? If I just keep throwing zeros in front of a binary number, does it hurt anything?
No, 0.
0 times some giant number plus 0 times some giant number plus 0 times some giant number doesn't impact the overall value, right? So we might need to pad the left-hand side with extra zeros. What that means, though, is it would be potentially detrimental for you to start taking your packs of 4 from the left.
So
You could start from the end, because if you start taking them from the left, you might be left with like 2 left over at the end, and then you know, okay, I didn't have a power of 4 number of bits to start with. All right, so we'll take it from the end. So our packs of 4 here will be 1, 1, 1, 1. So that's this first one. Then 0, 0, 0, 1. Then 1, 0, 1, 1. Then 1, 0, 1, 0. Just so happened I didn't have to do any extra padding in this case. All right, so I was able to take these in 4 buckets, then convert each of these into their hexadecimal equivalent. This is an 8, 9, 10, 11, so that's a B. 11 converts to a B. This is an 8 plus 0 plus 2, so this is a 10, which is an A. Final answer is AB, 1, F. So that's the hexadecimal equivalent of this scary binary number.
Okay, we're using base what again for this? 16?
Hex is base 16. Hex is the name for base 16. Hexadecimal. Octal is the name for base 8. Binary is the name for base 2. Decimal is the name for base 10. After that, most of them are kind of made up names. Those are the ones that are commonly used. All right, but to your point, if I wanted to convert this number, let's just take this exact same slide, and I want to say octal, we would take groupings of 3. So I'm going to actually go ahead, and just for my own sanity, I'm going to space it on 3s. Okay, so here's a good example. I need to take this first one and pad it with a couple of zeros. It doesn't change the value of it. Does that make sense? 0, 0, 1 is the same thing as just 1.
Octal is base 8, right?
Octal is base 8. Okay, so now I'll write out my packs. 0, 1, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 0, 1. All right, so this guy is a 7. This guy is a 3. This guy is a 4. This guy is a 5. This guy is a 2. This guy is a 1. So that is 1, 2, 5, 4, 3, 7. Octal. So 1, 2, 5, 4, 3, 7 octal is equivalent to this big binary number. Does that make sense? Does that make sense? Now, if I really hated you, and I said convert this from binary to base 21, now you have reason to be mad. Because you can't do the little grouping trick anymore.
Why not?
Well, base 21, what are the legal digits of base 21? 0 to 20? No, forget about that. Just 0 to 20 for numeric values. How many bits do I need to represent a 20? So the largest value in base 21 is a 20. How many bits do I need to represent a 20? So this is the 1s place, 2s, 4s, 8s, 16s, 32s. So that's too many. 1s, 2s, 4s, 8s, 16s, probably 5 bits. So a 20 is the 16s place plus the 4s place. So isn't that a 20? 1s, 2s, 4s, 8s, 16s. So this is 16 plus 4 is 20. Correct? Okay, well, an issue we have here is we can represent larger values than 20 in 5 bits. We don't have a perfect fit here. We can't do the little groupings trick. 3 bits allows us to do exactly base 8. 4 bits lets us do exactly base 16. 5 bits lets us do, this is 16 plus 8, which is 24, plus 4, which is 28, plus 2, which is 30, plus 1 is 31. This would let us do base 32. So the next base that we could do the trick for would be base 32. I call it a trick, but it's more just a compatibility. That makes sense? The one after that would be 64 and stuff like that. So that's kind of why we see things jump in powers of 2. So once the next logical step for us would not be, if we needed a larger number system in computing, the next logical step would not be to go to from base 16 to base 17. It would be to go from base 16 to base 32. Because that gives us the optimal translation between the bases. Does that make sense? Okay. So, kind of a handy trick that you might find helpful in the homework assignment coming up or something. I don't know for sure, but maybe. All right, so let's write the solution to your homework today, which was hexadecimal string to decimal, correct? All right, and the trick to that guy, again, I'm calling it a trick. Where's my atom? Here we go. So last time we wrote binary to decimal. We wrote octal to decimal. Okay, then we were to write hex to decimal. Now notice the difference between binary to decimal and octal to decimal was just how we maneuvered the place. Place always started off at 1, whether we were going from binary to decimal or octal to decimal. But as we moved to the left, we multiplied it by 2 for the binary. We multiplied it by 8 for octal. We'll multiply it by 16 for, let's just steal this code here for a moment. We'll throw it down here. Place starts at 1. Sum starts at 0. This guy takes it as something called a hex string instead of an oct string. But instead of multiplying it by 8, we're going to multiply it by 16. Right. So the issue we have here is this value right here sometimes is going to produce a value larger than, well, when we get the, I understand what you were saying. You were saying we need to change that to hex string. Hex string at bucket I will not always be something that is convertible into an int. An A is not going to convert into a 10 like we'd like it to. It'll convert into the Unicode value, Unicode version of a capital A, which is, what is that, 30, 37 or something like that? 30 something. But whatever. You know, not the 10. It's going to be a number much larger than 10. So we need to take whatever this hexadecimal character is and get the numeric value out of it. That is to say, when I have just write this like this. When I have the character 0, I should get the number 0. When I have the character 1, I should get the number 1. ... When I have the character A, I should get the number 10. The character F should give me the number 15. That make sense? All right, so we need a trick. We need to find a tool in our toolbox that gives me something like that. Okay, anybody figure out a fun way of doing that based on something we've already learned in class? Any suggestions? What suggestions do we have? Go ahead.
List out all the values from 0 to F, and then you just use their position.
So you created a string like this, right? And then if I was looking for, so where is A in this guy? If I were to search for the character A in here, it would find A at bucket 10, right? This is at bucket 0, bucket 1, bucket 2, bucket 3, bucket 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That make sense? So if we assumed our hexadecimal string used uppercase hextets, uppercase hexadecimal characters, then instead of saying convert this to an int, we would instead say something like, let's call this guy hex map. And this will be 0, 0 through 9, A through F, like that. And what we would do instead, I'm just going to steal this guy here real quick. What is it? String find, like that. I would say find in the string hex map that character. So this is the string I'm searching within. Here's the character I'm searching for. If it happened to be the character 0, it would find it at bucket 0. If it happened to be the character 5, it would find that at bucket 5. If it happened to be the character A, it would find that at bucket 10. Does that make sense? So this would give me the numerical value of that character, assuming hexadecimal. Now, if you didn't know about the find function, so let's test this real quick. Are we running anything else up there? So we're converting this guy to decimal, so let's go ahead and we're going to print hex to decimal of my favorite hexadecimal number, BAD. So it's going to pass in the string BAD here, and it's going to go through and it's going to figure out what the decimal equivalent of that guy is, which is 2589, I believe, is what that guy is. I didn't just convert it. It's my favorite one, so I use it pretty often. But I'm only about 97% certain I just told you the right answer to it. But we'll see here in a second. That's the whole getting old thing. All right, so we'll go ahead and run this. 16. So it doesn't like this guy. Oh, because I have a extra. Yeah, I need an extra closing parentheses here at the end. The find is a function, so there's the opening and closing parentheses for find, and then I multiply place by that guy, so there's the closing parenthesis for place. So, 29.89. 3% was the killer there, wasn't it? That is the right answer, 29.89. All right, so that converts a hexadecimal string into a decimal string, or a decimal number. Now, understand, though, that this is going to give me a very different value incorrectly. Since I passed it in as lowercase, I didn't adhere to our assumed standard of uppercase letters. It's not going to find lowercase BAD in here, so it's going to keep returning -1, right? So str.find returns a -1 if it does not find the value. So I'm going to get negative numbers in here. Added up. So this is not going to give me an accurate result. Now, one thing I could do if I wanted to cheat a little bit, let's say, is I could say something like hex string is equal to hex string dot to, I think it's to upper. Or is it just upper? Might just be upper, yeah, something like that. So this happens to be another tool that exists where this will give me the uppercase version of whatever hex string is, guaranteeing it's an uppercase. So it is a function. So upper is a function. So this is saying take this string, call his upper function on it, which converts him to uppercase, and move on with life. Not important for us right now. If your code only works for uppercase letters or only for lowercase letters, unimportant for us. That doesn't break our practice of problem solving. Because that's really what we're doing right now, is we're drilling our problem solving. Okay, and some of you saw in some of the comments, I have your homework grades up from the last assignment. You'll see in some of my comments from that, I gave you points if you solved it using a shortcut. I think one of you actually said, here's the working version that cheats, and here's the one I couldn't figure out. And that's okay. I mean, I would rather you struggle with it and then find a workaround. You know, you kind of run to Home Depot with the, this will be an ethics thing. You run to Depot with the credit card that you know has enough balance on it to buy what you need, take it home, fix what you need, and return it saying it didn't work. Okay, don't do that. It's bad. But you know, punchline is that I really encourage you. I want you to solve the problems that I'm giving you with the tools that I've introduced in class. There's a reason for it. There are easier ways of solving every one of these problems I'm giving you. But if you go and find the easier way, you find the right power tool, you're not learning. If you kind of put this in the context of maybe real life, if you build a house out of a hammer and nails and a screwdriver, you'll really, really, really appreciate the power tools that you might use to build the next house, right? So it's kind of that type of thing where I care more about you going through the effort and grappling with the tools that are in front of you, trying to do the MacGyver thing, you know, building an airplane out of the lawnmower and the tarp that's in the garage, rather than going out and finding every power tool that's out there. And then also the other risk to that, and I'm sure some of you ran into this, is usually it's pretty clear to me if you submitted something that you probably don't understand why it works. You know, you found some code on Google, you typed it in, well, this solves the problem, you submit it. I mean, that's fine, you're only hurting yourself. But, you know, the thing is, if you're using somebody else's code, it's not even about the plagiarism side of things when it comes to programming. You're shortcutting yourself by not learning that problem solving. You know, you didn't spend the 2 or 3 hours you needed to grapple with that to get it. And I realize that you don't want to just spend 3 hours in your homework because it's not fun. But if you want to become a good programmer, then turn that into a good high income and stuff like that when you get through school, this is kind of the price you pay. You know, we just put out a report this last week that right now computer science is the number one paying discipline with a master's degree, and it's number two with a bachelor's behind engineering across all disciplines. So put in the time now and you'll make good money later. Okay? And I realize I'm not going to be your best friend today. That's okay. I don't need to be your friend. Okay, we'll be friends later. All right, so does that make some sense? All right, questions about the solution to this one? All right, so your next assignment for Wednesday, I'll start it off here, and I'll put up the solution to hexadecimal, is going to be decimal to binary.
Isn't binary just 0 and 1?
Yep. This guy should return the binary string version of the decimal num. For example, if I passed it a 10, 10 should produce the binary number. This is an 8 plus a 0 plus a 2 plus a 0. So it should produce that string. The binary number, the binary equivalent of 10. Now remember, this is the one where we divide this number over and over again. So we divide 10 by 2, we record the remainder. If you want to see this real quick in our last moment, you can pack up because I know we're out of time. But if I say 10 to binary, this is 10 divided by 2. 2 goes into 10 5 times. 5 times 2 has a remainder of 0. 5 divided by 2 goes in 2 times. 2 times 2 is 4 with a remainder of 1. 2 divided by 2. 2 goes into 2 one time. 1 times 2 is 2 with a remainder of 0. 1 divided by 2. 2 goes into 1 0 times. 0 times 2 is 0 with a remainder of 1. We know we're done when we finally get a quotient of 0. We read our answer from bottom up. This is 1 0 1 0. You will be concatenating these results, these remainder results together as you go through. Remember that the the remainder operator is the percent symbol. That's modulus, right? That gives us the remainder of an integer division. 5 mod 2 gives us a 1. 5 divide 2 for integer division will give us the 2. 2 goes into 5 2 whole times with remainder 1. Make sense? So I'll post the solution to the homework today, and I'll post the starting point for the next thing, but that's due on Wednesday. All right, have a good one.
So, just to double check, you want us to use actual math to do it and not like a dictionary that just...
Correct. Yeah, I haven't introduced dictionaries yet.
Okay.
Yeah, use math.